So Johannes Kepler had a good mathematical mind and a strong faith in the accuracy of Brahe's work. So basically what he did is continued Brahe's work, and he made three laws of the planetary motion. The first law of what he did was the elliptical path around the sun. And you can see right here how they are all moving in an elliptical path. The second law was that the planet orbits around the sun at different speeds, and you can see how they're all moving at different speeds. Please don't relate to this because it's not to scale. And the last law that he made was that the planet's orbital period squared is to its mean distance cubed, and you can see the formula right there. Now, the two main motions of Earth are rotation and revolution. Rotation is the turning or spinning of a body on its axis, and you can see how the world is kind of spinning around. And then revolution is the motion of a body, such as a planet or moon, along a path around some point in space. And you can see how it's kind of moving around the sun. Rotation is based on the day and night. And what day is the time between sunrise and sunset. And it's basically when the world is kind of rotating around the sun, and you can basically see everything during the daylight. And night is the period of darkness between the sunset and sunrise. It still has that tilt of the axis, but it's just still like rotating around the sun, and that's when it's hitting the other southern hemisphere. Now, revolution is basically when the Earth revolves around the sun in an elliptical orbit at an average speed of 107,000 kilometers per hour. And you can see kind of how it's moving in an elliptical form around the sun. And at perihelion, that is when the Earth is closest to the sun, which means that it's going to be moving faster. And you see how it's kind of moving a lot faster. And aphelion is when it's farther from the sun, and that means that it's going to move a lot slower than perihelion. And you can see how it's kind of moving slowly, but it's still making progress. And you can see how the Earth is still moving slowly around the sun. I recommend getting yourself comfortable. It's going to take a while for that Earth to make a whole full 360-degree circle. Now we're going to talk about Earth's axis and seasons. The imaginary plane that connects Earth's orbit with celestial sphere is called the plane of ecliptic, and you'll see right there. The apparent path of the Sun and the celestial equator intersect each other at an angle of 23.5, and you'll see it right there. From a northern hemisphere point of view, these intersection of the spring equinox, which is right there, is during the March 20th or 21st, and the autumn equinox is during the September 22nd or 23. On June 21st or 22nd, the date of the summer solstice, the sun appears at 23.5 north of celestial equator. And then 6 months later, on December 21st through the 22nd, the date of the summer solstice, the sun appears at 23.5 south of the celestial equator. And here's a better picture of the seasons. You'll notice that there's always that tilt, and whenever that tilt of 23.5 is hitting the sun, that means that we're either in summer or during the winter. depending on what kind of equinox we're in. And you'll see that when we're in summer, that tilt is directly hitting the sun, and when we're in winter, that tilt is away from the sun. That means that we'll have more cold seasons. And you'll see that every single time that tilt is always pointing the same way. And now we're going to talk about precession. Precession is a slow gyration of Earth's axis around the pole of the ecliptic caused mainly by a gravitational pull of the Sun, Moon, and other planets on the Earth's equatorial bulge. And you'll see in this picture right here how it's basically just going around in a circle. You see how the Earth's orbit is, and then that tilt of 23.5 is basically going around in a circle. And there's an example right there. Remember that we're always on that tilt. Now, nutation is a small periodic motion of the celestial pole of Earth with respect to the pole of the ecliptic. What it's basically doing is wiggling around. And you'll see that right there. And the difference between nutation and precession is that nutation is wiggling around, while precession is going around. Now remember that nutation, the change is 1 inch every 72 years, while precession, this occurs every 26,000 years, and the seasons will change.
So here we're going to give a second look at rotation. The spinning of a body of mass on its axis is known as rotation. As the Earth spins, it causes different sides of it to face the sun at different times, which will bring cycles of day and night. Oh, let's see in the example. So here we have the Earth rotating. It doesn't exactly rotate like this, but we didn't have a 3D model. So now, as you can see, the side facing the sun is day, and the side facing away is night. Oh, so it's here where we're discussing revolution. Revolution is the orbit of a body of mass around another. As the marker so eloquently puts it, the Earth's orbit around the sun is what causes seasons. You know, you have summer, autumn, winter, and spring. So that's how you get seasons. It's due to revolution. Oh, let's see how it goes. So here it would be summer in the northern hemisphere. There it would be fall in the northern hemisphere. There it would be winter in the northern hemisphere. And here it would be spring in the northern hemisphere. Oh, there's me erasing the board. Is that hand not the most amazing thing you've ever seen? Oh, anyway, the law of universal gravitation states that everything has a gravitational pull, which means that the moon has a gravitational effect on Earth, and that is what causes tides. So there you have the Earth. There you have the moon. The gravitational pull between the two causes tides to form. Oh, what a twist. And I erased the board yet again to introduce the new topic. So here, it's not really so much of an Earth-specific thing. It's more like a general thing. And oh, I cannot spell anyway. Basically, the circumference of any spherical object around its ends will always be smaller than when it is at the center of it. Because imagine you have an orange, right? Where the little green things at the end and no one knows what they're called, that's where the circumference is the narrowest. And around the center is where the circumference is the widest. And at this moment, I'm doing all of these hand gestures that I know you won't see, but oh well. So there you have the Earth, your big blue ball of life, and as I mentioned before, you can see that the circumference around the poles is much smaller than that of the equators. Oh, what a twist. Nuclear reactions. Nuclear fusion is the process of two or more atoms colliding to store energy. It's sort of like how the human body uses fat to store energy. Nuclear fission is the process by which these atoms split and are used as usable energy. This is how the sun and other stars survive. Radiation is how heat and sunlight get to the earth from the sun. As seen in this diagram, atoms go to the sun, fusion and fission occur to make that energy usable, and voila, it is radiated to the rest of space in the form of electromagnetic radiation. Oh. So it is here where we discuss differential heating. This occurs because water heats up at a much slower pace than land does. Therefore, you have higher annual temperature ranges in landlocked regions than you would in, say, a region bordering the Atlantic Ocean or the Pacific Ocean or the Great Sea or whatever, you know? So that's why that happens. So there you have the sun, there you have the land heating up very quickly, and there you have the water, which is sort of just chilling. So it is here where we discuss photosynthesis. This occurs when plants take in energy from the sun and use it to make glucose for themselves and oxygen for the world. You may or may not be familiar with this process. This is the sun. There's the plant. And there's the sunlight, which allows it to make glucose and oxygen. And lastly, but certainly not least, we have Earth's magnetic field and its function. It serves to protect the Earth by sending some of the more harmful solar radiation around the Earth rather than straight towards it. Now, obviously, all of the radiation isn't sent away from the Earth, but it redirects most of it so that we can live a safer life on this planet we call Earth. Get me emotional. But yes, there's the harmful radiation, there's Earth's magnetic field, and voila, it just slingshots right around it.
Okay. For how long?
Okay, alright, that's good. You're not recording it, are you?
It's a fat arrow.
Oh my gosh, Nelly.
Stop it. Keaton, what are you doing? Look at it.
Oh my God. Okay.
I have 28% left.
Oh my gosh. Okay. All right. All right. There, look.
That's a very skinny
I
arrow.
don't care. I don't care.
So it's here where we're discussing differential heating. This occurs because water heats up at a much slower pace than land does.